first thing, we're planning in a continuous space. So the first thing we do is we discretize this continuous space into a graph. I'm going to describe this in a second. We solve the corresponding problem of inspection planning on this graph. And then we incrementally update this graph to be more and more dense. Now, if you guys are familiar, who here has any background with motion planning, even the most basic background? So if I remove inspection out of these words and say motion planning, this is exactly like your classical sampling-based motion planning. Think of PRM, RRT. What you do is you sample your continuous space to create a graph. What is the, how do you solve the discrete planning problem here? It's a question to you guys.
Use A star.
You run your shortest path algorithm on the graph. Dijkstra, A star, whatever you want, right? And then you update this structure. So the question is, what is the equivalent of Dijkstra A star in this setting? And I won't give you the algorithm, but I'll give you a flavor, and then we'll see how this connects to the talk. So this is a definition of the analogous discrete version, the graph inspection problem, not in the continuous space. So instead of the robot's configuration space, we're giving this discretization, this roadmap. Think of a PRM roadmap. But now we endow each vertex in this roadmap also with a set of points of interest that we can see from that vertex. And we want to plan a path in this roadmap that sees as much points of interest as possible. What do we care about? We care about path length, which is just the sum of edge length. And we care about path coverage. If we want to simplify the problem, we can only obtain coverage at vertices. So we just take the union over all vertices in the path and say, what can we see from these vertices? And we want to compute the path that sees as much points of interest, which is as short as possible. So let's kind of get a flavor of what's going on. Let's say that this is the discrete version, this discrete roadmap. We have here vertices A, B, C, and D. We have edges, which edge length. And from each vertex, I tell you which points of interest that can we see. So from vertex B, we see point of interest 0. From vertex C, we see point of interest 1. From A, we don't see anything, and so on and so forth. What's an optimal inspection plan here?
Where are we starting?
Oh, at A. You always start at A. Sorry, I should have said that. Yeah, we start at A. Yeah, so you go to D, you return to A, and then you go to B, right? So this kind of gives you a flavor. So we collected, so if you look at the kind of animation, we start with a path of length 0, we don't see anything. We go to D, path length is 1, we covered the first point of interest. We need to return to A, we didn't see anything else, and we move to B. Okay, so kind of we may need to return to the same vertex over and over. So that's one problem that we're facing. The second problem is if we assume that there's another part of the graph here, and we need to compare the left path, the blue path, and the orange path, one has a length of 4, but sees points of interest 0 and 1, and the other has a length of 2 and sees the point of interest 0. Which one is better? I wish I could have your face here. We don't know. It depends on the future. And that's kind of the problem, that we can't take local decisions saying, when we do Dijkstra or A star, we look at two paths that reach the same point, and we say, this one is better than the other because it's shorter, right? And here, it depends on the future. If the next vertex is also going to see point of interest 1, then we don't need to do that detour through vertex D. If it's not, and that's the only way we can see point of interest 1, then we have to go to D, and the blue one is better. So in some sense, our search algorithm has to maintain both the blue path and the orange path. So we solved this, this problem using a new search algorithm. And the underlying problem was basically solving a bi-criteria search problem. We have two criteria here, path length and path coverage. And we're not sure, we can't really compare them. So we want to solve for all paths that are kind of manage the trade-off between path length and path coverage. And this got me into a rabbit hole of multi-objective search algorithms that I'm going to share today. And what I'm trying to argue is that this is another one of the algorithmic tools that we should have in our toolbox. Even if you don't understand all of the mechanics behind them, just like you would use shortest path in the arsenal of tools that you have at your disposal, multi-objective search is another one of these tools, especially given that now the algorithms have pretty much matured. So for the rest of the talk, I'm going to dive into the multi-objective shortest path problem. I'm going to give you kind of a crash course mini tutorial. The take-home message is what are the types of problems that we can solve here. So I'm going to give you several variants of this problem, and then you can choose to use them or not. At the end, for those of you who are interested in the specific types of problems, if we have time, I'm going to also share with you some of the challenges that we have and the things that we didn't solve in this domain. So now I'm taking my roboticist hat off and putting on my pure search AI hat, and this is different communities that speak somewhat of a different language. And let's give a very clean, formal definition of the problem without the robotics, inspection. So this is a kind of a graph search. And let's say, to motivate this, let's say that we want to take a bike tour in the northern part of Israel. That's where the Technion is located. So we want to take a bike tour from Akko to the Sea of Galilee. And if you go to Google Maps and ask, what are the options that I can take? Google Maps gives us 3 different options. Bottom, top, and middle. And you can see that each one has a different length. If we only cared about going from point A to point B fastest, we would take the top path. But if you look at the elevation gain, and I didn't know this, but Google allows you to look at elevation gains when you walk or take a bike, we can see that the top path has the maximal elevation gain out of the 3 different paths. If you want to get to your beach, the barbecue as fast as possible, I'm not sure if climbing the most amount of hills would be the right choice. And we don't know that as a user. So the problem is important beyond just going to the beach with your friends. These types of problems can be found in a lot of domains, basically balancing several criteria. For example, it has been used for transporting hazardous material, trying to balance travel distance and risk to where this material is being transported, and has a lot of applications in robotics. And once we identified this in the inspection planning problem that I kind of used at the beginning of my talk, we found that it can be used to balance safety and path length, or when you provide assistance to a robot, it can also be used to balance between several criteria. And it's not necessarily that at the end of the day, you need all these set of paths. Sometimes the search needs to track all the options, and only at the end can it make a decision which of these paths does it care about. So let's try to establish a common language, and from now on, it's tutorial mode. So if you have questions, stop me. If something's unclear, stop me. We don't need to get to the end. So if you remember, we had three different paths in our motivating application. And let's see how we can visualize them. So each path has its own travel time and has its own elevation gain. So we can think of a path as a two-dimensional point where the x-axis is travel time and the y-axis is elevation gain. Obviously, smaller is better. We want shorter paths, and we're lazy, so we want to minimize elevation gain. And if we look at the first path, we can put it on a point here. If I look at the second path, pi 2, we see that it has longer travel time, but lower elevation gain. So where is it going to be relative to pi 1? So it's going to be to the bottom right. Which one is better? We don't know. Where's pi 3 going to be? Yeah. So pi 3, in some sense, is worse than both of them. So if a path is worse in both criteria, it's going to be to the top right. Okay? So now we can formally define what's going on. If we have a graph, with two cost functions. These are our two criteria. And we have two paths that reach the same vertex. We say that one path dominates the other if it's better on both criteria. So basically, every path in this region is said to be dominated by this path. Okay? Since we have a collection of paths, what we want in these type of problems is to compute the Pareto-Frontier, or the set of all paths that no other path dominates them, or that they collectively dominate the entire region. So in this setting, the Pareto-Frontier is the lower envelope, basically this set of paths. Are the definitions clear? Okay, so again, all the problems that we deal with are at least NP hard. This problem is also NP hard. And if you look at the related work, either existing algorithms try to really compute the entire Pareto-Frontier, or relax the problem and compute a subset of the Pareto-Frontier. And I'm going to talk about both variants throughout the talk. The problem is that the Pareto-Frontier can be really, really big. What is really big? If you have a graph, it can be exponential in the number of nodes in the graph. So things become really sad really fast. Let's start step by step developing algorithms to solve this problem. And again, you don't need to follow all the details. Some of it is going to be a bit technical. The take-home message is what you would care about. The first algorithm that I want to solve, and everything that I'm going to talk about, this is, I think, the earliest algorithm that I'm going to talk. So everything is 2020 and onwards. This is really the state of the art in the field. So the first question that we want to ask is, if we compute the entire Pareto-Frontier, how can we do it efficiently? And when we say efficiently, we need to ask, what's the bottleneck? And the thing is, because we have a Pareto-Frontier that is really, really big, a key operation that we'll have to do is test for dominance checks all the time. We always have to do dominance checks. And that is the computational bottleneck in most of these algorithms. When you do dominance checks, basically you have two vectors, and you want to compare the coordinates, the pointwise coordinates of these vectors to see if one is smaller or equal than the other in each one of the coordinates. Now, everything that I'm going to talk about, 90% of the talk is going to be on bi-objective, but everything that I'm saying is for the multi-objective setting when we have more than two criterion. It's just easier to visualize and to talk about two objectives. So I don't know if I wake you in the middle of the night, you can write the pseudocode of A star. But if you squint your eyes, what we have here, which is bi-objective A star, is the A star algorithm. So let's squint our eyes and just say we have some initialization step. We have an open list. We store the open list in some order. At each point, we remove the node from the open list. If we reach the goal, we're happy, we're going to store it. Here we need to keep on running because we don't have one specific goal. We need to enumerate the entire Pareto-Frontier. And then what do? We ask what are the successors at this point. So for each successor, we create a new node, we populate its fields, and so on and so forth. And here we have some, basically this line that I skipped when it said that this is the A star algorithm is asking, is this node dominated by another node, or is this node dominating another node? And kind of the key to efficiency of this algorithm is the realization that if you store nodes in lexicographic order, so you go from, and the first objective, you go from low to high. If that's the case, the first objective, we call it the G1 value in the A star literature, but let's think of the first objective. If we know that the first objective goes up, because we store nodes in the open list lexicographically, so that cannot decrease. In order for this node not to be dominated, what do we have to do? We need to find a node whose second objective is lower, because we know the first objective is going to be higher. So if a node is not dominated, we only need to look at the second objective. So what do? We just need to store for each vector the minimum value for the second objective already found. And when we do dominance checks, so this is kind of the initialization where this is for infinity. When we do dominance checks, we only need to compare the second node. In this case, it's a scalar. In the general case, we reduce the dimensionality from d dimensions to dn minus 1 dimensions. This has a dramatic effect on the running time of these algorithms. So great, we know how to compute the entire Pareto-Frontier efficiently. The question is, do we really need to compute the entire Pareto-Frontier? And I argue that it's a waste of time. So if I give you two paths, and even when you look at your app, if I give you two paths that differ by path length by 1% and differ by safety or coverage by 1%, for all practical purposes, they're the same. And if you run these algorithms, they're going to enumerate all these exponential number of paths. And in some sense, we want a diverse set of paths. Okay? So let's look at approximations of the Pareto optimal frontier. So we're moving from exact solutions, which is what I described earlier, to approximations. For that, we need to kind of extend the taxonomy that we developed. So if you remember, we said that this path dominates everything else in the blue region. We want to extend strong dominance to also say, if you're slightly better than me, for all practical purposes, I still am allowed to dominate you. How does this correspond pictorially here? This is a question. So basically, I allow some buffer zone that I can say that this path also approximately dominates things that are close here. Mathematically, what does it mean? If dominance said that one path is better than the other in each objective, it says that it's not too far away. So if I add epsilon, let's say that this is 1.1, so I allow 10% slack. Basically, it says that I'm not worse than the other path by at most 10% in each objective. Okay, this is the definition of approximate dominance. So now, we have the definition of the Pareto-Frontier. Now we can extend it to what's an approximation of the Pareto-Frontier. And basically what this means is we want a subset of the solution on the Pareto-Frontier that collectively, approximately they dominate the entire Pareto-Frontier. In layman's term, what does it mean? Basically it says, I give you a subset of the solutions, and any other solution that I didn't give you is not too far away from one of the solutions that I did give you. Now the question is, how do we compute this? Yeah?
Why do they need to be on the Pareto-Frontier?
They don't have to be. I can give you, and some of the algorithms that we do give you points that are close to the Pareto-Frontier, but some still have the same property. I'm cheating. I'm lying constantly throughout the talk. Okay, so this is the definition of the problem. We want to compute approximation of the Pareto-Frontier. So let's try to develop the algorithm here together. So just like in the algorithm that I described, VO A star, we'd like to run something like A star, and every time that we found two nodes that are practically the same, we'd like to throw one of them away and only keep one representative. And that is going to allow us to maintain less nodes in our search. If I found one node that is approximately better than the other, can I throw it away? And the answer is no, and we can really visualize this pretty fast. So let's look at this kind of toy graph. We have here, from the start to the goal, 3 different paths. We have the path that goes through V2, through V1, and the direct path from the start to the goal. If we plot them, these are the numbers. And I may have made a mistake, but I think these are the real numbers. And let's say that we compare the yellow path and the purple path. And we say that pi2 approximately dominates pi1. So if we throw this path away, basically it means we don't keep track of that, and only keep track of v1. And then we have the situation where we compare pi3 with pi2, and we say pi3 approximately dominates pi1, and we forgot that we threw pi1 away. Then we threw a path away that is not approximately dominated by one of the solutions that we return, and we broke our promise to the user that we're going to give them a good approximation. So in some sense, we need to track all the paths that we threw away. If we need to store them, it kind of defeats the purpose of doing an efficient algorithm. So the question that we need to ask here is how can we throw away paths while still storing the fact that we had them, and what would have happened had we kept on using these paths. So basically what I want to say is I'm giving a subset of solutions. I want to keep only one representative path, and I want to maintain, to store the fact that all of these solutions are what are represented by this path that approximately dominates all of them. And what we're going to do is basically say we're going to store the top left path, the bottom right path, and everything in between we can throw away. And we only need to store two paths as long as collectively they approximately dominate all the paths. So instead of associating each node with a path, we're going to associate each node with what we call a path pair, top left and the bottom right. Now we're going to say that such a path pair is epsilon bounded if basically the top left and the bottom right are not too far away. If the top left and the bottom right are not too far away, anything in between can't be too far away, right? Because they're in between. So basically we want the figure to look something like this. Now what are we going to do? I'm going to describe this algorithm waving my hands. We're going to run an A*-like search. Nodes are going to be path pairs. Every time two nodes reach the same point, we're going to ask ourselves, can we merge them? What is merging? Basically saying we have something like this. Top left, bottom right, top left, bottom right. We're going to take the top left out of the two, the bottom right out of the two, these two guys, and ask, is this still epsilon bounded? If the answer is yes, great, we can merge them, and we kept track of everything that the first path pair and the second path pair kept. And then when we finish this search algorithm, within each path pair, we just choose, say, the top left. This is the visualization. So here we have kind of a degenerate path pair that only consists of one node. So top left and bottom right were the same node. So sometimes this is more inefficient because we don't get any information. Here we have 3 nodes in this path pair, the red one. And here we have 4 nodes. And then we return just one representative path from each path pair. So we run this algorithm, compared it to a variant of VOA star that does approximation, and we get a pretty nice speed up. The speed up changes with the approximation factor. This shouldn't surprise us. When there's no approximation factor, then you don't get any, this epsilon, this approximation doesn't help you actually do more work because you're maintaining more information per node. When the approximation factor is huge, then basically you only return one solution, and then any algorithm that does something semi-intelligently can throw away almost everything because everything is epsilon dominated. But where things are interesting, if I tell you I only want solution, I want to get a 10% approximation factor. So only give me a subset of the solutions, but I want it to be a pretty good approximation, then we can get a 6, 7, 8x speed up in this case. How are we doing time-wise? Okay. So this was my work. And then I came to collaborators and they said, you did it. It's nice work, but you did it sloppily. Let's clean things up. Let's do it properly. So let's do things properly. But I think from an educational perspective, this is easier to kind of explain. When we wrote this first paper, we proved that what we do really provides an approximation. In this proof, basically we said, if we have a point that dominates all points in this Pareto-Frontier, it's basically the pointwise minimum of the top left and the bottom right. And in the proof, we call this an apex that dominates the entire path. And then Han, a student at USC that I started working with, said, instead of storing the top left and bottom right, let's store the apex and a representative path. It seems like potatoes, tomatoes, what's the difference? Why do we care about this difference? So he suggested an algorithm instead of using path pairs, using what we call an apex path pair, so storing the apex and storing the path. And then we coined the term, instead of A star, and we have apex, so it's A star X. There's no other name that we could give to this algorithm. And we could do exactly the same thing, run an A star-like search when possible, merge between apex path pairs. So we see here an apex and a path, and then merging, but just taking the minimum of the apexes. So it's essentially the same algorithm, just a different representation of a representative solution and how we control the entire Pareto-Frontier. And the question is, what's the difference? Why do we want to go to this machinery? I'm going to speed things up. So the first reason is kind of technical, and I'm going to skip it. The second reason is more important. The algorithm that we developed is very natural for 2 dimensions. And then we thought, okay, for future work, we'll think of having not a top left and a bottom right, but now we have a 3-dimensional space, and we need 3 representative paths, and how do we scale with the dimension? But if you think of the apex as the representative of the entire Pareto-Frontier, regardless of the number of objectives that you have, you can use one apex. So this is my lousy attempt of drawing a 3-dimension. So think of this kind of jumping out from the board. The apex is one single apex. It dominates the entire Pareto-Frontier, which is now this manifold in 3D, and we only need one representative path. So this...
Why do you need a representative path?
Later I need to return to the user something that he can use. So what's cool about the apex is basically saying, I pretend that it's a path because I draw it on this 2-dimensional or d-dimensional axis, but it's not realizable. It's just a lower bound on the set of all solutions in the Pareto-Frontier, or the subset of the Pareto-Frontier. But I also need to give the user later something. So again, we compared it. I'm going to use a lot of these figures. They seem a bit daunting at the beginning. Let me finish. And basically what we have when we compare 2 algorithms, I have the running time of each algorithm on the x-axis and the y-axis. And then I run the same experiment for each algorithm, and then I can plot it as a 2-dimensional point. When they behave exactly the same, the running time of both algorithms is equal. It's going to be on the diagonal. If one algorithm is better, then it's going to be, so if our algorithm is better than the alternative, it's going to be to the bottom right. Everything here is logarithmic. So here we have 1x improvement, 5x, and we get up to 50x. So that's the way to read these types of figures. As the dimension increases, the power of this technique also increases. We had a question somewhere. Yeah?
I just want to follow up on the previous question.
Can you speak up?
Yeah, I just want to follow up on the previous question. How do you pick the representative path?
It doesn't matter. Choose one. I mean, we have strategies, but it doesn't make a big difference, and it's not that important because they're all the same. Essentially, the philosophy is it doesn't matter because they're all the same. Okay, so I dove into 2 different applications, or 2 different instantiations of the multi-objective search problem. We talked about computing the entire Pareto-Frontier, and we talked about approximating it. I'm going to be nice to you and not go into a third one, but I will mention the types of problems that we can solve. The first one is anytime multi-objective search. So if I don't have time to compute the entire Pareto-Frontier, but I want to give as much of the Pareto-Frontier as possible, given a limited amount of time, then I'll run an anytime search algorithm. So here, we look at the approximation error that we get. How well can we approximate the Pareto-Frontier as a function of time? And the anytime, the solid lines are the maximal error, the dashed lines are the average error. And notice this is on the New York map where we have three objectives: the cost of going through a path, the time, and the distance. And we can see that we can get a really good approximation, much better than the alternatives. And kind of the machinery that we use under the hood is the approximation algorithm that I talked about, the A-star test. Why is that interesting? Usually, if you remember at the beginning of the talk, I told you that a powerful tool that is shared among state-of-the-art is ordering nodes lexicographically, because that gives us the ability to do dimensionality reductions. If we store nodes lexicographically, how will we find solutions? Also, the solutions are going to be found lexicographically. So we go from the top left and we slowly expose solutions along the Pareto-Frontier. Which means if I ask, how many solutions have I found in the first 3 seconds, they're all going to be here. And then I give solutions here, here, and here. So the algorithm, in some sense, doesn't give us, if I need to stop him early, it's still an anytime algorithm, but it approximates too well the top left side of the Pareto-Frontier and really badly the bottom right of the Pareto-Frontier. And if you think about the approximation algorithms that we use as the underlying building block in these anytime algorithms, what they do is they compute an initial crude approximation, so they kind of sample sparsely the Pareto-Frontier. And if you give them more time, they're gonna densify their approximation. And then, in the first 3 seconds, we found solutions here, and then in the second 3 seconds, we found also distributed solutions, and that's why the machinery that we developed can easily be applied to these anytime algorithms. If your problem has, you need to run multiple queries, so you have a multi-objective search problem, and you're going to run a lot of queries on it, you can actually do some pre-processing. This pre-processing is pretty expensive computationally, but we assume that we can have time in advance. And then you can get dramatic speedups. It's not really fair in the comparison because there were no algorithms that could, that did any pre-processing in multi-objective search. So we can get 100x speedup. So this is if you're a PhD student and you want to run a plot with 2-3 orders of magnitude speedup, just choose a problem that no one else looked at, and then you don't have a baseline, and then you can get really good improvements. So this is one of those examples. There's also the setting of bounded cost. So if I say I want to compute a solution on the Pareto-Frontier, but I want it to be below some bound on one cost, so I want it to be below some path length and at least as safe, then I want one of these solutions, then we can apply, reuse the same machinery that we talked about in order to compute one representative solution. Okay, so we're coming towards the end of the talk. If any of this is relevant to your work, either from kind of, I'll call this a practitioner point of view, where you want to use this as an alternative to shortest path in your research, or if you're interested in these types of problems, we recently had a paper in Dijkstra. They have this survey track, I think it's called, where we talked about research progress and research opportunities in this field. And the way this paper is structured is we first give an overview of what are the types of problems and the algorithmic building blocks. So I mentioned here dimensionality reduction. We formally define why is dimensionality good and how is it used. We give a mini overview on the related work that the community has developed. And then we talk about recent advances and open challenges. All the stuff that we found too hard to solve, basically we said someone else help us out. How are we time-wise? So I think I'm going to skip the first one in the interest of time. If we want, we can later go back. It's talking about heuristics. Just like an A star, when you have heuristics, it's basically a point guiding you towards the goal. And multi-heuristic A star and multi-objective search, the heuristic is a bit more complicated because it needs to capture all cost functions. I'll just give you the figure without explaining. Usually you have one value that needs to kind of dominate the entire Pareto-Frontier, but you can do something fancier and have a heuristic that has several values. It sounds kind of weird, so the heuristic is going to be 2 points. It is very powerful in guiding the search on the one hand. On the other hand, it's hard to compute, and then standard tricks are not applicable, so dimensionality reduction kind of goes out the door when you use these kinds of things. So an interesting question, without me explaining too well, is how do you compute these and how do you effectively use them? So these are type of the questions that we pose in this paper. Another one which is much easier to explain in the last few minutes and is surprisingly important is I told you that we order our objectives in lexicographic order. And we didn't say which order, which is the first objective, which is the second objective. And it sounds like a silly question. So we looked at the best algorithm that we had, and we looked at a road network with 3 objectives: time, distance, and economic cost. And we looked at 3 different orderings of these objectives. We were super surprised. There's a difference of, so here we have, on one instance, it took 11 seconds versus 1.5 seconds to compute the entire Pareto-Frontier just by changing the ordering. Why is choosing economic cost and not distance important? I don't know. We have some hypotheses, but this is an interesting open question. And we see this both on easy problems and on hard problems. Here, between the worst ordering and the best ordering, there's like a 5x difference for the same algorithm. So it's just how does it expose the structure of the Pareto-Frontier. So obviously a challenge that we pose to the communities is how to choose. And it's more interesting not how to choose, because you can do something quick and dirty to learn the specific domain, but why does it matter? And can we use algorithms that exploit this structure? And we don't have any good answer to this. So if you're interested in these types of problems, this is a great research problem for you. There's no good solution, so going back to my comment earlier, if you find any good answer, it's going to be the best answer out there. There are other challenges understanding correlation in a lot of domains. We pose this as a multi-objective problem, but if you look at roads, usually travel distance and traveling time are correlated. There is a correlation between the two. So there's a lot of underlying structure to the problem. Can we exploit that algorithmically? Can we understand it? We know that if the objectives are perfectly correlated, so if I have a multi-objective problem, but at each edge, I take the first objective is just the second objective multiplied by 2, it essentially collapses to a single objective problem. If I just add white noise to 1, so they're perfectly correlated up to white noise, I can still get an exponentially large Pareto-Frontier, but it's going to be very, very close, so it's going to be easy to approximate. So the whole notion of correlation is super interesting. We don't understand anything about it. These algorithms have a huge memory footprint because they store the Pareto-Frontier for each individual node, either the entire Pareto-Frontier or a subset. So memory footprint is a huge issue here. Parallelization is embarrassingly underexplored in this domain, and how to do it intelligently is also something open. So I think this is a good place to kind of conclude the talk. I said we because what happened historically is I got sucked into this through the inspection planning problem, and then we had this amazing collaboration with the guys who wrote BOA Star. We basically joined forces and got into a series of all the works that I described and many more. Sorry, Alfred and Sven Konings are the PIs, but people who are doing the heavy liftings are the PhD and Carlos Hernandez, who's a professor, but he does a lot of real work and not taking credit for other people's works like I do. And obviously the funding agencies. So with that, I'd be happy to take any questions, and thank you.
Thank you, Oren. This was very interesting, and I'm sure there's a couple questions in the audience. Brian.
So one way to get the representation algorithms is sometimes introduce randomness in the algorithm. And I'm wondering which parts of this algorithm would benefit from that. It seems like the risk of rapid ordering might be one of those places. I'm wondering more about where would you introduce randomness and would get some probability there and the expectation of the algorithm.
So that's a good question, and the answer is, I don't know. Randomness could help to avoid understanding the problem in some sense. There's been an algorithm that basically says, instead of going lexicographically, no one asks why not go lexicographically the other way. And if you do it, or you and randomly chooses, it goes simultaneously in both directions. In some sense, that's a way to cheat around understanding which ordering is better and to average the actual randomness, and I think that's why we have to speed up in that algorithm. So I'm not sure about, definitely it can be used to average bad decisions and good decisions in these types of algorithms, which is one step.
Yeah, so it doesn't come over balance.
Yeah. So definitely we can do that, and we can build kind of either randomly or simultaneously, so that it's a different form in some sense of randomness. Do a lot of decisions when we don't know what's the right decision to do. So definitely we can use that. Where else can we use randomness? Maybe in dominance checks. So there's a good question, an interesting question of what is the right way to do dominance checks, what's the right data structure. So there are fancy data structures to do dominance checks. A lot of time they're not worth the extra computational effort that they introduce, because you need to maintain balanced trees, and this is in a high dimensional space, so you need to do space subdivision, and sometimes just a linear ordering is good. If you do things linearly, then maybe randomly doing it, again, would average, because you don't know what's the right way to do dominance checks, not ordering nodes. So that's an interesting place where we can introduce randomness and dominance checks, especially if we do it linearly, because then we can make a really bad decisions on what the order is and get screwed with that. Yeah?
Thank you for the really interesting talk. I was curious at the problem of using like probabilistic edge costs as considered. So like for example in surgery, you might have, you want to minimize the distance you are in the body in that travel, but each different passageway can have a different risk factor to it. And you want to basically find a Pareto-Frontier such that you constrain the maximum variance or some risk factor to that.
So we're looking into some variant of that problem, and where you basically want to balance average risk and path length. I'm not aware of anything, but that's an immediate application. These are kind of the immediate questions, and sometimes we as algorithmic developers don't know the preference. So when would you use this? Let's go way back to the motivation. Computing the Pareto-Frontier, or an approximation of the Pareto-Frontier, is when we want some decision maker to give us one option of using it is to give a decision maker the trade-off when we don't understand how he balances the different objectives. If we knew how to collapse, at the end of the day, a surgeon in your example would choose one path, but we don't know how he has a cost function that maybe is a non-linear combination of the different objectives. And if we knew that how he combines the different functions, we would say, okay, we want a path that is this much risk and this much path length, and then we'd have a single objective search problem. Since we don't know it, we want to provide it to the surgeon, and then we say, these are the trade-offs. Now you articulate your preference. So that's the whole reason why we want to compute the Pareto-Frontier approximation. Yeah.
Awesome talk. It seems so extreme to project Bellman's principle of optimality outright at the beginning. I'm wondering if there's like some problems, some practical problems, where you don't need to start with such an extreme position. So like you took this inspection problem as the motivation at the beginning. But I can imagine a long path where I'm doing inspection. And the things that I can see at one end of the path are disjoint from the things that I can see at the other end of the path, just for practical reasons, right? And then you can imagine, well, what I do over here actually has nothing to do with what I do over here, and some version of Bellman's principle of optimality will be restored.
So
Can you account for that in this framework?
So the answer is at least two. First of all, approximation or merging different paths basically makes that statement a bit more fuzzy. If it's almost the same, then I don't need to keep track of it, which is good enough. The second is, I think a lot of the problems that we have structure. And this is a very pure definition of it. And even in road networks, we talked about it, path distance and time are highly correlated. So I think in a lot of practical applications, we don't really have this multi-objective search problem. But because we don't understand the structure of the problem and correlation, what you're talking about is spatial correlation in your search problem. And first of all, how do you define that formally? That's a good question, which we're interested in, and how do you explain it? So I don't have a good answer, but definitely it's a right observation.
Thanks.
So in regular A-star, your heuristics need to satisfy the velocity and disability.
There's a real echo when you talk, so can you...
So in regular A-star, your heuristics have to satisfy the velocity and visibility. And I'm wondering if in multi-objective A-star, those properties change, or do you just apply them element-wise in your multi-value heuristic? Is there any other constraint that the heuristics have to satisfy in this case?
So I'll give an annoying answer in some sense. The premise was inaccurate because in A-star, we know what happens when admissibility / consistency don't apply. In one sense, we don't get optimal, so in one part, we don't get optimal solutions. In the second, we do, but we may need to re-expand those. And there's ways even to use these frameworks without admissible and consistent heuristics. There's multi-heuristic versions of A-star where we have maybe one inadmissible heuristic and one admissible, and you kind of use them together to guide the search. So there's ways to circumvent admissibility and consistency. In this case, usually we don't really understand, we don't do a good job as a community in understanding the extra power that heuristics have in this domain. So I kind of alluded to it here. The most common heuristic that we've been using in the community is the following one. Let's run a shortest path, a single objective shortest path for each objective. So in this example that I won't go over, but we have the shortest path according to the first objective is 3. You can double check me while I'm talking. And for the second objective, it's 3. Usually all the examples are symmetric. And then you can say, so this is the shortest path when I optimize for cost 1, and this is the shortest path when I optimize for cost 2. And what's going to be an admissible heuristic? Basically take the pointwise minimum for both of them. We call this a point heuristic and a single value heuristic. Clearly it's admissible and consistent, but it's highly uninformative. So what can you do better than that? Up until now, we as a community have been using 99% this heuristic, which is the simplest one. It has one value, it's consistent, and it's admissible. And we didn't explore too much stronger you're relaxing these strong requirements, and what are the pros and cons that we can get? So that's the answer.
So this example reminds me, or gives me an idea about, so your heuristic here is an apex, right? And so can you, but your epsilon is not defined. And so can you turn it around and say, can I now search for an epsilon such that
I mean, for this specific version, we computed these two guys. So actually we know how bad this heuristic approximates. So we're a bit better than not knowing anything. So we know how good the apex approximates the entire, we know that the entire Pareto-Frontier lies between these two points. So it's not totally uninformative, but we don't know what we can do with it much better than that. It can give us a bound on the initial epsilon to use. We know that we don't need to start somewhere here because this is a bound. So this is really good for the anytime algorithm, how to choose the first epsilon and then how to divide it. But at least now we're not doing anything fancier than that.
Any other burning question? Okay, I'm sure Oren is going to be around for the next 1.5 hours. So if you have a question or a student want to talk to him more personally, that's probably an opportunity you're going to have in the next 1.5 hours. Other than that, I thank you very much for coming today and attending the seminar. This was the last seminar of the season, so we're going to resume back in January, I believe. Have a good rest of your day and happy holidays.